think for some of the audience, right?
It's okay. Just don't say anything bad about anybody. It's all recorded. So.
Ooh, okay.
Okay, YouTube is going. So.
Thanks, Joseph.
Your speaker is off. I don't hear anything.
Really? Joseph, can you hear me now?
Now I can hear, yes, but before I couldn't.
I guess we were just not saying anything.
Oh, you're not saying anything. Okay.
Yeah. Yeah. So I guess we'll start, right? So welcome everyone to this seminar. Yeah, we are pleased to have Christoph Uhlemann from the UB, who's going to tell us about a way of exploring doubly-holographic CFTs. Please take it away.
All right. Thank you very much. Thank you for the invitation. It's great to be here at such a beautiful time of the year. So my talk is going to be about exploring doubly-holographic CFTs, where double holography is an extension of the usual notion of holography, which has found some interesting applications recently in black hole studies, but it's also applied much more broadly. And the idea for the talk is to focus on the CFTs that are underlying this extended notion of holography. And hopefully at the end of the talk, report some new results which we can get for these CFTs by neatly combining holography and field theory methods. And nevertheless, sort of along the way, a good part of the talk I want to spend on reviewing and introducing this concept of double holography and its realization in string theory, which gives me a nice way to introduce the theories I'm going to care for. And as per usual, please feel free to interrupt and ask questions at any point. If I don't make it through the slides, that's just fine. Okay, so why do we care about double holography? In the context of black hole studies, we've certainly learned a lot of interesting things over the years, not in small part due to ADS-CFT on holography. And this usually involves some sort of idealized set. In the context of supersymmetric black holes, we can account for the Bacon-Stein-Hawking entropy of large classes of black holes indirectly by either counting brane-bound states or relatedly in ADS-CFT computing supersymmetric indices in the dual field theories. Both of these things are happening far away from the parameter regime where black holes exist, but the results can be extrapolated to actually account for the entropy. So that's one part. And then we're, of course, at the epicenter here for the program of constructing explicitly the microstates underlying this entropy in the relevant gravitational regime in the form of supergravity solutions and increasing fractions of the entropy. So these are some very nice avenues to make progress here. When it comes to studying dynamical aspects, so black holes also far from extremality, a different type of idealized setup has recently come into focus, and that is you take a black hole in its gravitational environment and you couple it to some non-gravitational reservoir, some kind of bath. And what this does for you is it gives you a place where you can, let's say, collect your Hawking radiation or do other things. You could define observables or computables within the safe environment of a conventional quantum field theory. So that gives you a place to formulate question, and then for actually computing things, That's where the concept of double holography comes in, makes these setups tractable and computable. And the claim to fame of these kinds of setups is, of course, the computation of page stress or Hawking radiation. As all idealized setups, these setups come with fine print, which I don't want to get too deeply into here. But this is certainly a nice environment to study all sorts of questions related to black holes. Okay, so that's basically the idea. Describing these kinds of setups is one of the applications in the context of black hole physics. And what I want to do now is sort of introduce the concept of double holography and go a little bit through the motions and mechanisms behind it. So the basic idea was conceived some 25 years ago in the context of bottom-up toy models, which are kind of nice and intuitive. And so I think it's a good idea to go through this with a little bit of hindsight and spend the slide on. So starting point is some conformal field theory defined on a spacetime with the boundary. I'm going to refer to this boundary frequently as defect. Whatever is on there will be referred to as defect degrees of freedom. The idea is to reserve the term boundary more for holographic concepts. Okay, so then that's our first kind of description, the field theory side. And the idea now is to apply holography twice to these setups. In the first step, you could imagine just taking whatever is living on the defect and dualize it into a gravitational description. So pictorially speaking, what we do is we draw out an extra holographic direction and replace what's on the defect by an ADS4 gravitational theory. So this is exactly the kind of setup that I was talking about. We have some gravitational theory living on an ADS4 space, which is coupled then to the leftover ambient CFT, which functions as the reservoir. So that is the first time to apply holography. You can then hope that if you're lucky enough and the setup allows for it, you get to apply holography a second time and grow out an additional radial direction out of the ambient degrees of freedom. And wouldn't it be nice if the holographic dual were just defined by filling in this space, which is not shaded here, with an ADS5 geometry? So that is the third description. In the setup, you have ADS5 gravity with an end of the world brane as an extra ingredient, which basically chops off space. So that's basically the setup. We have our nice theory lab in this description B, where we have gravity coupled to a bath, can throw a black hole in here, collect the Hawking radiation out there completely.
So this another world brane, is it the deep brane or is it some other defect?
Very good question. Give me 1 minute and I'll come to exactly that. Okay, this is sort of very nice leading into the next slide. So for now, this is what I'm saying. Sort of B is the setup where you formulate the problem, and C, where you have this full bulk gravity, is where you do your computation. But the problems you're setting up are still hard to tackle, and so that's the way to go. Now, this was a bottom-up model, and as usual, they come with caveats. And here the caveats are that neither of these ingredients live in string theory. These are not D-branes. This is some bottom-up tangent pole object, which you throw into some 5-dimensional Einstein gravity. There's no microscopic definition. And likewise, what I've drawn here is a schematic representation for some CFT. It's not microscopically defined quantum field theory. So this is different ways of saying the same thing. The CFT is not microscopically defined. This is not a UV complete gravity setup. This is one of the and what is slightly bothersome also is that there's no general reliable dictionary relating all these three descriptions, which is certainly something you would want to have if you want to reliably translate your calculations between these different. So those are some of the things one might not be terribly happy about, but this does what the toy model is supposed to do for you. It gives you a good idea. And so the next step then is to sort of isolate the basic idea out of this cartoon and make it yourself. So let's formulate what we actually want in terms of quantum field theory language. And what we want here is not all that little. We want some BCFT, CFT with a boundary, which is fully holographic, and has on the defect, on the boundary, additional genuinely lower dimensional degrees of freedom. So not something which you get from restricting ambient operators to the boundary, genuinely new degrees of freedom. You want to be able to isolate those out of the BCFT so that they can be a quantum field theory in their own right. So I can write a decomposition in this form. then these 3D degrees of freedom should separately be holographic. Right? So if I have all these ingredients, assuming you grant them to me, then I can dualize this thing separately, the 3D degrees of freedom, and what I get is my gravity coupled to a path description, and I can dualize the whole package of field theory data, which should give me some gravitational dual, which somewhere far away from the boundary starts to look like ADS5.
Is there a stress energy tensor only in the 4D CFT or also in the 3D? What are the stress energy tensors?
Good. So you have a combined stress tensor, which is conserved.
Yes.
And then you have, due to the coupling between the 3D and 40 degrees of freedom, you do not get a separately conserved 3D stress tensor. When I'm saying I want this to be defined as a field theory in its own right, I'll specify what I mean as I go along. And please, if that's not clear.
Because you're saying you have ADS for gravity, like usually we say, no, when we have ADS d plus 1 gravity, that's like having a d-dimensional stress tensor. But in this case, there's probably no three-dimensional stress tensor.
This is one of the fine prints that are coming with these setups. Due to the fact that you don't have a separately conserved stress tensor, you don't get a mass described on there. That's the story. Okay, good. But sort of as far as things go, this is making a little sharper or formulating in a different way this cartoon which I just had. And the idea is I want to come back to this as we go along. One important aspect here is that I want this ADS4 gravity and this 40 ambient degrees of freedom similar, in some vague sense, similar numbers of degrees of freedom. One of them shouldn't just be a probe. I want to be able to dial them independently. So that means whatever is living on the defect should be fully back-reacting, both in field theory terms and in the holographic sense that the geometry is affected. Now, I'm not aware of a general characterization of what kind of CFTs can do this for you. Something along the lines of what we usually say about holographic CFTs, for spectrum of low-lying operators and so forth. But there is an example class of theories which does just that. So for now, I don't need to care and can just move on and argue that one can actually make every step in this construction precise. And then this gives me this construction of double holography as I want it. Okay. And nice as it goes, the class of theories which you can start from. 40 is n equals 4 superunions or favorite theory, and introducing a boundary or a defect or interface or something like that to n equals 4 superunions allows you to preserve at most half of the supersymmetries. And what kind of boundary conditions you can put was classified in beautiful work by Gaiotto and Witten some 20 years ago. In string theory terms, what you do is you terminate 3 branes on 5 branes. And the simplest example is you just terminate a whole stack of these 3 branes on a single NS5. That gives you a supersymmetric version of Uhlemann boundary conditions, preserves the right supersymmetries, but it doesn't give you any genuine 3D degrees of freedom, which weren't there to begin with. So that's not quite what we want to do. We want to do something slightly more involved. And the next best thing you can do is evenly spreading these D3 branes over a whole group of NS. This preserves the same symmetries, and it now gives you non-trivial 3D degrees of freedom. Basically, each of these finite extent stacks of D3 branes gives you a 3-dimensional gauge node. So you get U1, U2, U3, U4, and so forth until you eventually couple to the 40 CFT node. So that's the notation I'm going to use, a bunch of 3D gauge nodes. And then one gauge node with a head is a 40 n equals 4 superunions node on a head. So this is almost there. This gives me now VCFT with non-trivial boundary degrees of freedom, but I'm still kind of bounded by how many 40 degrees of freedom I have in what I can make. If I start with some number of D3 branes, I can't crank this up beyond what I've been doing. But this is easy to generalize, and this leads to the general picture, which looks something like that. You have a number of D3 branes. They terminate on several groups of D3 branes suspended between NS5 branes. You get D5 branes in addition, which are shown as these red lines at an angle. And they basically introduce fundamental hypermultiplets associated with the field. So I get a generic 3D quiver of this variety, which is then at the end coupled to a 4-dimensional gauge node. And in this setting, I can really now crank up the 3D degrees of freedom independently of whatever I have in coordinate space.
The number of NS5 have to match the number of D3s.
No.
You could also have that. Could you have just taken many more NS5s, no D5s? You have n D3s, and could you just take n squared or many more NS5 than they have D3s and no D5s?
So there are some constraints for the, if you want a nice infrared fixed point for this 3D gauge theory, which basically is saying that all gauge nodes should be at least balanced. That's then there's the specification to good, bad, and ugly. And if that rings the bell, so there are some mild constraints on what you can do here. But basically, relative to these semi-infinite D3s, you could take them all away and just look at a 3D CFT and go. So there's no constraint here. Very good. Good. So yeah, the point is this gauge theory is not conformal yet, but you flow to the infrared fixed point of this thing, which is the strong coupling limit, and that gives you an actual BC. Okay, so these are the field theories we care for. And of course, we want to do some holography shenanigans with them. So we're going to need the holographic duals. And the nice thing about these theories is that they are generically known, explicitly known how to construct the holographic duals. They are to a large degree determined by symmetry. You get an ADS4, which represents the 3D conformal symmetry that you want to preserve. You have two spheres representing the remaining R symmetry. And then the rest is sort of two unconstrained directions, which is really where the interesting things are happening. So basically, these unconstrained directions encode the brane construction that we started up. So for the theories we care for, we can take this sigma, this remaining Riemann surface, to be an infinite strip. On each boundary of this strip, one of the spheres collapses so that the geometry closes off smoothly. And then you have some distinguished points at which the 5 branes emerge, which were involved in the brane construction that we started. So each of these marked points corresponds to a group of D5 or NS5 branes. And how these D5 and NS5 branes are distributed over the boundary of the Riemann surface encodes the 3D degrees of freedom, what exactly the quiver was that we had on the previous sheet. And then last but not least, semi-infinite D3 branes give rise to a direction in which the warp factors in the geometry blow up to produce an asymptotically ADS5 cross S5 solution. So that's basically the setup we're working with here. There is a precise identification between the parameters in these gravity solutions and the field theory data. And these duals are also extensively tested through supersymmetric localization, increasing levels of sophistications. So these are really reliable dual descriptions for the kinds of theories that I've introduced. Okay, so basically we have everything in place to take this little cartoon that I was making there and put meat on it in terms of concrete field theory. So here I'm showing on the left the kind of simplest setup, which does everything that I want to do. We have some BCFT, there are semi-infinite D3 branes. I have a 3D quiver where the rank sort of first increases from gauge node to gauge node, and there's a maximal rank node with flavors to them attached to it, and then the rank goes down, and eventually I'm connecting to the 40 degrees of freedom. And I have to sort of specify how I'm going to do this decomposition. I have to isolate the 3D degrees of freedom out of this BCFT. And the way to do this is you can do away with these D3 branes by just terminating them on a group of D5. So in Kröder language, you replace this 40 gauge node, which was here in the BCFT, with just a 3-dimensional flavor group. And that then defines the 3D degrees of freedom. And if I want to go from this picture back to this picture, I have to gauge this flavor symmetry using n equals 4 superangulates on a half. Okay? So that's just sort of following the Gaiotto-Witten construction, going from this 3D CFT in isolation to a BCFT on the left. And I have to remember, of course, that if I want to put an equal sign between them, I still have this floating around, which I have to do. Okay, nicely enough. We also have the holographic duals for these theories. As I was trying to advertise, in this case, we have one group of NS5 branes, one group of D5 branes, One group of D5 is just the fact that there's one 3D node with flavors attached to them. One group of NS5 has to do with the fact that all these gauge nodes are balanced in this construction. Could have made it more complicated, but there's no need. So just one group of NS5s in the holographic dual, and then an ADS5 cross S5 region for the D3. On the right-hand side, for this kind of setup, the holographic duals can be taken from the same class of solutions. We have done away with the semi-infinite D3s, so ADS5 cross S5 disappears. But what you get as a trade-off is a second group of D5 in the holographic dual, because there are now two gauge nodes which have flavors attached, one in the center and the last one. Okay, so these are basically all the ingredients that we need to formulate this double holography. Put meat on this double holography schematic version on the top. And the only thing that we basically need to specify now to complete the story is to give a holographic dictionary relating the different descriptions. We have this decomposition. We have exactly defined how the coupling between 3D degrees of freedom above works. So the only remaining step is to put this into one coherent dictionary. And this can be done in the usual way by, this can be done in a convenient way, at least, by translating this construction into a path integral form. So I'm just using on the left-hand side, I'm writing so this equation. Basically, the idea is to write the BCFT partition function in a convenient way. I'm going to suppress the sources here, but the idea is to write the BCFT partition function by starting with the 3D CFT partition function. It has a flavor symmetry. That's the one I'm caring for, which has a conserved current associated with it. And associated with this conserved current is a background gauge field, which is the source of this conserved current. Non-dynamical background field from the 3D perspective. But I can now formulate this gauging by identifying this 3D gauge field as boundary value of 4-dimensional gauge fields. This should be a dynamical gauge field, so we're going to integrate over it and put as measure the n equals static element. That's just a schematic path integral representation of what we've done in the previous form. And now all I need to do is use the standard Z equals Z holographic dictionary, which tells me that the BCFT partition function is identical to the string theory partition function on backgrounds which are specified by this asymptotics, possibly with additional sources turned on, depending on what I want to compute. But that is the idea. And I can also apply the same logic to this 3D CFT partition function, replace it with the string theory dual. So this is now.
May I ask a question, please?
Sure.
Did you take any sort of IR limit in order to have that? Because to have the 3D gauge, to have a 3D CFT, it's only in the IR that it's true, right? When all the branes collapse to a point and everything. So where did you take it in this picture, or?
Yes, so this for the brain picture here, I sort of separated out the 5 branes. But the idea is that what I'm talking about here really are the CFTs. So I want the regime in which this thing is dual is described by this solution is the regime where you're taking the strong coupling limit, the strong coupling IR limit. So all these field theories are considered in the at the fixed point.
Okay, thanks. Yeah.
But the fact that you have a flavor symmetry that remains in the IR limit. You get additional symmetries, but sort of nothing really hinges on having this gauge theory picture.
Okay, thanks. Yeah.
Good. Sweet. So we have our gravity theory coupled in some particular way to the ambient CFT. That's the intermediate picture that we formulate our questions. And we have the full holographic dual. And all these things, the only things I needed to use was the standard Z equals Z ADS CFT holographic dictionary. No esoteric ingredients. It's basically standard constructions as far as that goes. Now, explicitly evaluating this dictionary, that's a handful. Of course, it's not super straightforward, but there is something which you can see right away by just staring at these geometries in detail. And that is that if you wanted to sort of in the bottom-up construction, we had our end-of-the-world brane, and basically all three descriptions lived in the same picture. We had gravity coupled to the ambient CFT, and then the full BCFT dual just filling it in, everyone living in the same picture. So here, would be the analog of having the end-of-the-world brane, basically, the gravity on the end-of-the-world brane. And you can ask, does this geometry fit into this full BCFT dual in any meaningful way? And it just doesn't. The geometries are different throughout, and that is sort of perhaps not entirely surprising, but if you take a 3D CFT and you couple it to some 4-dimensional ambient CFT and then dualize the whole package, you're going to change the holographic dual for the 3D CFT too. Okay, that's just what happens. And this brings me back to the picture that I had on the initial slide. It's important to really keep these holographic descriptions separate. I have sort of let's say this is the holographic picture where I formulate my question, where I have gravity coupled to a dot, and then I have this guy who is the full BCFT dual, and I should really look at them as linked to this underlying BCFT. There's no simple pictorial identification between the full dual and this defect dual, where you just say, okay, I take part of it and hack away an ADS5, and then I retain my gravity coupled to a dot description. And that's kind of an important point, because this very fact that in bottom-up you have these descriptions all living in the same picture leads to causality paradoxes before you even introduce black holes. So this is sort of a very clear way in which these some paradoxes or puzzles which plague these bottom-up models are avoided in these top-down concepts. Okay, so that hopefully explains that part of the title slide, and it also sets up sort of the program for me. If I look at the page curve calculations, for example, the way they work is you formulate the problem on one side, you do a computation over here, you get some entropy curve consistent with unitarity, great. But what one really wants to do is sort of understand what's happening in this, what is physically happening in this description where I actually formulated the problem. So I would have to translate everything back through this underlying code representing the BCFT with this dictionary I explained to understand what's actually going on. Questions like, are there islands outside the horizon? Can one connect this to some microstate understanding, perhaps, of the black holes we're looking at? This is a full string theory setting, so in principle, one can ask these kinds of questions. And this needs very good control over the individual dualities and how they are linked with each other by this double holography. Now, the point is, these individual dualities, as I tried to advertise, they're very explicit. They are extensively tested, but they are a handful to work with. We have non-trivial walk geometries. All the type 2B fields are turned on. Basically, a lot of things you touch immediately blow up in terms of just doing that. So for that reason, even though many things are known, many things have been compared, partition functions, standard operators, there are also lots of things missing. And that basically brings me to what I want to talk about. Some recent results in this regard, and brings me to the outline. So the outline for today, hopefully I motivated a little bit that these kinds of theories, n equals 4 super Young mills, fully back-reacted defects or boundaries, whatever, are an interesting class of theories to look at for these very reasons. But there is work to do, and I want to tell you basically about 3 things, and depending on how time goes, they are somewhat self-contained. Please continue to ask questions, we just capture whatever. So the first part is about the very intimate relation between these supergravity solutions and the matrix models that arise from supersymmetric localization in the dual field. There's a connection between them which goes well beyond what you're guaranteed to get from ADS CFT logic. And this relation turns out to be useful, so I want to advertise it a little bit. We'll then, in the second part, use this relation to get the first non-trivial correlators for these kinds of theories, defect one-point functions, protected operators, and any super Young mills. And in the last part, I want to then switch gears and talk a little bit about also non-protected things, tell you about some insights into the spectrum of these theories, where there are some surprisingly highly symmetric sectors among the operators in these VC. That connects to the BMN story, and I'll tell you a bit. This is all based on these papers. The first two with Dongming He, he's a grad student in Brussels, and the second one with Andrea Cheney in Michigan. Okay, let's get to it. First, let me make this very explicit. They are very earthbound and straightforward reasons to care about these theories. Simple fact is that no actual physical system is translationally invariant. Always some boundaries, impurities, and whatnot. So there are certainly very different reasons as well, which I didn't dwell on so much, for studying these theories. And I could have just as well made this all about boundary and defect CFTs. In some sense, these theories I have been introducing are like the harmonic oscillator of 4D boundary, defect, and interface CFTs. In the same way that n equals 4 superioris, the standard version of it is sometimes called the harmonic oscillator of 4D. One of you. Maximally symmetric theories, non-holographic dual, the best control you can hope. Okay, we have on the right-hand side the defects in their own. We have a BCFT here, and the only step you need to take to generalize this to interfaces, let's say between n equals 4 superioris, with different rank gauge groups, different couplings, is to introduce a second ADS 5 process 5 region into the supergravity solutions and the other things. Generalized straight up. So as I tried to say, as much as you can hope for, and yet there is a lot left to explore. And I want to tell you a little bit about what one is. Okay, so the first part is about a connection between the supergravity solutions dual to these theories and the matrix models that emerge in supersymmetry. So let's approach this step by step. Certainly, any holographic duality which is worth its money, should lead to an agreement between field theory calculations and gravity calculations. That's what ADS CFT guarantees for me, and that has been tested extensively. Beyond that, I'm basically on my own. There's no need for these theories to agree along the way on computational steps that you're taking at intermediate stages. They only have to agree on observable. But sometimes you can get lucky, and this is such a case. So to spell this out, I'm giving you here the supergravity solutions with a little more detail. The point I want to make is that everything about these solutions is defined in terms of a pair of harmonic functions on the Riemann surface, on the signal. So you see here the metric, the dilaton, they're expressed in terms of some composite quantities, N1 and 2W. Doesn't matter. Eventually, they're all expressed in terms of H1. So this is the data which the BPS equations tell you these solutions are specific. Similar expressions for the fluxes, which I'm not giving here. But the basic idea then is that you have these harmonic functions. Getting regular solutions imposes constraints on them. And if you solve these constraints, the parameters that are left behind are what connects to the brane construction and ultimately. And the claim now is that this pair of harmonic functions, which came out of a purely gravitational problem, solving BPS equations, this and that, actually are the saddle points dominating the matrix models that you find when you do supersymmetric localization in the dual field. That's as direct as the connection can be. So let me tell you how this comes about. To do this, I need to first talk a little bit about localization for these theories, and want to show that in some sense, the data that you have on both sides is compatible in its mathematical sense. Okay, so we're going to look at this kind of theory, completely sort of a generic thing. And the holographic limit we're talking about here is the limit where you have large numbers of D5 and NS5 branes. And this in quiver terms means you get many three-dimensional gauge nodes. It's a long quiver. You have many gauge nodes. They all have large ranks, or almost all have large ranks. The ranks can vary, but that's the limit we're looking at. And now we're going to do our localization game, which means we replace path integrals by finite dimensional matrix integrals. And going through the mechanics here gives you one matrix integral for each of these statements. We get a matrix model, a whole lot of matrices, and some mighty complicated integrand, which encodes the one-loop fluctuation on the field around the localization. Okay, so then we go through the usual kind of story of localization, of working through these matrix models. We go from the matrices, the eigenvalues, eventually to eigenvalue distributions. And the point now is, which is kind of fun about this large n limit, is that if you take this family of eigenvalue densities, one for each gauge node, you can assemble them into a collective field of two variables by just taking an effectively continuous coordinate along the quiver. And so you get a family, you get one function of two variables. And this function effectively behaves like an electrostatics potential when you look at the saddle point. So there's an algorithm basically for translating the field theory you're looking at into an electrostatics problem, which is defined in some cavity, where in the interior you have point charges, conducting plates, things like that, which are determined by the features of the three-dimensional field theory. Where do you have flavors attached? Where do you have unbalanced nodes? Translates into this kind of thing. And the n equals 4 super Young-Mills nodes appear as non-trivial boundary. And this is what you want to solve to get the saddle points dominating the matrix model. And once you have that, you can compute a lot of things just right away from the saddle point. So on the gravity side, we had two harmonic functions, H1 and 2. Here we have one electrostatics potential, also harmonic function. So there's at least some chance to make these things. And I want to sort of give you a one-slide idea of how this match works. The idea is to derive a relation between, not guess it or observe it, but derive it. And the way to do this, of course, is to go through actual observables for which you know that they're linked by ADS-CFT. So in this example, the particular class of observables I want to look at are Wilson loops in antisymmetric representation. There are reasons I can certainly do this, so let me just go with it. There's a whole family of these observables. For every gauge node, I can look at a Wilson loop in the antisymmetric representation. In the brain construction, this is represented by a D5 brain with K strings attached for rank K antisymmetric. It's a family of observables. I get a two-parameter family from a node in rank, and I can find these D5 brains in the holographic dual. So what's happening here, each of these blue lines gives me a probe D5, which represents the Wilson loops that I'm working through here. And I won't go through the details of what exactly they wrap and how they're embedded, but the point is, by identifying Wilson loops associated with individual gauge nodes with these D5 brains, you get a set of coordinates on the Riemann surface, which have a field theory meaning. Each of these blue curves corresponds to one gauge node in the field, at least as far as these observables. And I can now go ahead and ask, okay, how would I reproduce these Wilson loop expectation values on the field theories? On the field theory side, a rank K antisymmetric Wilson loop just picks out the K largest eigenvalues. So from that, you know that these Wilson loop, the collection, this family of Wilson loops, encodes the cumulative eigenvalue distributions for each and every gauge. The mighty indirect relation, because I have to go through these probe brains, calculate on-shell actions to get expectation values, the whole game, but the information is in there, and all I have to do is extract. And what's somewhat remarkable is how simple the relation is in the end. So just going through these mechanics, one can solve for the eigenvalue distributions in terms of gravity data. And what you find is that one of these harmonic functions, H2, gives you the field theory coordinates on the strip. So that's eigenvalue and gauge node label. Defines the grid, which I had on the previous slide. And then the other harmonic function just gives you the value of the eigenvalue distribution at that corresponding. So at the end of the day, in that sense, these harmonic functions defining the gravity dual are the saddle points. If you have one, you can just go to the other. If you look at the matrix model, you don't see the saddle point, you can go to the supergravity setting, determine the saddle point from there, and the other way around. And the nice thing is, by going through this whole process, we have a relation which is derived, so it's reliable, and we can use it to really find saddle points for field theories, which we didn't know the saddle points. Okay, to give one example, I can look at a generic. I'm going to just assume that this quiver is balanced. We can give the completely general saddle points. They are mildly obnoxious in that they involve some special functions, some generalized Lambert function, but it's a reasonably friendly one. It's just defined implicitly and easy enough to deal with. And these kinds of saddle points can be derived independently from the matrix models and from the holographic data. On one strike, we get a whole new set of consistency checks where we can compare between field theory calculations and gravity calculations. And just to give a flavor of what these precision tests look like, this is the simplest BCFT, the kind of thing where we uniformly distribute the decrease over 5 branes. They're the parameter K. I'm not going to explain these expressions in detail. Point is, there's some polylogs in there, as generalized Lambert functions. This is the kind of thing you can derive independently in field theory and gravity and really compare that data. So this is as good as it sort of gets for these theories in terms of U1 decision. U1 is a complex parameter which is defined implicitly here. These expressions simplify if you look at 3D CFTs. Basically, this funny K is the rank of the Wilson loop representation. Z is the coordinate along the 3D banknotes. And then basically one has to go through this to actually get an instant. It's in some sense just an alternative parameterization. You can parameterize the Wilson loops in terms of Z and K, or in terms of. Okay, good. So that's precision test. And when you have precision tests, you can then put things to work. And that is what the multi-section is about. Okay, so let me tell you about one-point functions in theory. And start from the beginning. We have CFTs with interfaces, boundaries, defects, and the simplest non-trivial correlators you can look at are the one-point functions. In flat space, they are functional form is fixed by symmetry, basically gives you the denominator, but the numerator gives you non-trivial dynamical information, assuming you can normalize the operators independently. And so that's the natural first kind of target to go after when computing correlation functions. There's a lot of work has been spent on looking at these correlation functions for simple defects. So let's say a probe D5 brane in ADS5 process. Something where on the left and on the right, you have almost the same theories, just a sort of perturbative change as you cross an interface. In these settings, one-point functions have been studied using probe branes in string theory, integrability methods, localization. Lots of work has been done there. And the idea now is to sort of go at it and extend these results to fully backreacting rich defects. And the way to go there is by combining localization and supergravity. Basically, the strategy is this. In principle, you have the holographic dual. You can extract the one-point functions from this holographic dual. Okay, so if you follow the recipe. But here we have some mighty complicated backgrounds with warped geometries, all the fields turned on. You would have to actually expand things, decouple them, do holographic renormalization. It's conceptually straightforward, but it's not something I would prefer to spend time on. On the other hand, in the matrix model, once you have the saddle point, computing one-point functions amounts to putting a little insertion in there and just integrate. So the strategy is we take the holographic duals, find the saddle points, and then get the one-point functions by just evaluating an insertion. So let me tell you what kind of operators we're looking at. Generally, when we have a defect, the 40n equals 4 superangle fields decompose into representations of the 3D defect conformal symmetry. You get a 3D vector multiplet, a 3D hypermultiplet. Basically, the 6 scalars split into 2 groups of 3. But we have an SO3 from each of them. And what localization gives you access to are some particular twisted translated combinations of these 6 scalar fields. So to do localization, we have to map the theory to a 4-sphere or a hemisphere. And then which operators we get access to depends on where on the hemisphere we're looking. So we're going to look at the North Pole. And then it's basically something like x plus iy. Combination of these. That's an operator you can look at. And there's a straightforward way to fix the normalization of these guys from the 2-point functions in unmolested anything for super young mills. And then basically this is following standard procedures. There is a slight subtlety where sort of this map between sphere and flat space introduces some mixing, which has to be undone, which gets some additional subtleties when you look at backreacting defects. Let me not go into the details here and just show you, give a flavor of what the results in the end. So the simplest defect I can look at is I just take n equals 4 super young mills, same rank, same coupling on both sides, and I intersect the D3 branes either with a stack of NS5 or a stack of D5. Intersect them with NS5 branes, I get a set of 3D gauge groups. So these guys here, if I intersect them with NS5 with D5 branes, I get a set of 3-dimensional hypermultiplets localized on a defect. So this is the kind of setup which has been studied extensively. Okay. 4 branes in the usual Torch limit, the 1-point functions for this, for the probe limit were computed already well, with a reasonably simple form. And we can now just blow this up and get you the fully backreacted defect 1-point functions. What happens is, like this. So these simple expressions become some generalized hypergeometric functions. There is an additional parameter, which is how many D5s, NS5s do you put relative to the D3 branes. You put a D5 defect, which is this thing, with an NS5 defect, this thing. The point is, we can recover from these results the probe limit. We get the correct behavior on the S duality, which basically swaps these curly D5 and NS5 numbers with each other. So we have some nice consistency checks and can have some confidence that these results are. Okay. So that is that part. I'll tell you about 2 more examples without giving you expressions. The pattern basically is that you start with simple expressions like so, and you blow them up in some complicated generalized hypergeometrics. But one of the setups which has also been studied extensively is where I now allow for different ranks of the gauge groups on the 2 sides of the interface. If I put NS5 branes here, that means I just get a string of 3D gauge groups where rank decreases. If I put D5s, that they impose some non-pole boundary conditions on the D3 branes, which reduces the rank as I go across. Again, this has been studied some 5 years ago for a single D5, where I terminate some of the D3 branes on it with some general non-pole boundary conditions. And we can now, again, in the setting where we have consistency checks, generalize this to fully backreacted defects. Results satisfy the expected S duality relations. So we get some nice consistency checks here. The last example, emboldened like this, lots of consistency check, is a case where we don't have anything to check against, but are the theories we actually care for. These CFTs that were underlying the construction of double holography, where I terminate D3 branes on a combination of NS5 and D5 branes. There's not really a good probe limit here, because terminating the CFT is not a small deformation anyway you look at it. But we have enough confidence in the methods and the consistency checks that we can now claim we have the first correlators for the doubly-holographic CFTs, which give us a target also for this intermediate picture that where I have gravity coupled. One of the things that would eventually be nice to do is do precision tests on the double holography dictionary itself. There we had our 3 different descriptions. And first I need some targets to actually go there. So here we have some one-point functions in the B CFT, and it would be nice to reproduce these one-point functions in this gravity coupled to a bath description that I was saying. So that's the first target, or one additional target, if you wish, for things to come. Okay, how are we doing on time? I started a little late, I think.
Yeah, so I think you have like 15 minutes.
Okay, good. That should be fine. Good. So that was that part. We talked about the connection between these hologravity duals and the matrix models. Derived it, put it to work to get some one-point functions. In the last part, I want to talk about the spectrum of local operators in these theories. Now, again, once you have a holographic dual, you should expect that you get a lot of information about the spectrum just from that. All you need to do is find the KK spectrum on your background, and that should translate to the spectrum local operators in the dual C. Unfortunately, here you have to go through, you have to decouple all the gravity modes, and then in the end, you still have to solve PDEs on sigma to actually get the harmonics and translate this to the spectrum of local operators. Some people looking into this using things like exception field theory, which is an interesting avenue to pursue. But what I want to basically advertise here is sometimes you can do simple things and actually get some very nice information too. And that leads me to the discussion of BMN links. Okay, BMN like sectors. Let's start with n equals 4 superangles. Famously, there's a very nice sector in the spectrum of operators identified by these gentlemen there, BMN, which basically can be set up as follows. You look at operators with large R charge. So you start from some seed operator, which is a single trace operator, trace Z to the J, where Z is some combination of the scalar fields and any superangles. The BPS operator, you know what the spectrum is, no surprises here. But the interesting piece of information now is that this operator has a lot of friends, operators which are in some sense nearby. You view this Z as a string of J-Z operators. You now start one by one flipping them for other fields in n equals 4 superangles. And it turns out you can precisely get the spectrum of all these non-BPS operators. Flipping them takes you away from the BPS limit. You can get a precise expression for the spectrum from string theory, which I won't discuss in great detail, but it depends on how many operators you insert, whether you include phases with these operators. You get supergravity modes, springy modes, you can get all those. And the intuition behind this is that operators with large charge correspond to strings which zip around the S5 with large angular momentum. And if you boost the strings hard enough, they will just experience the geometry near a null geodesic zipping around S5. And the geometry near null geodesic, something Penrose's limit, gives you a 2D wave solution. And on that, you can solve the string theory. Okay, so that's in a nutshell the review. And the idea for going through it is to set this up for the solutions that I've been.
Is the answer at large n, but exact in lambda? Normal dimension.
Okay, good. So this is the story in standard n equals 4 superangles without any extra degrees of freedom. And now naively, if you look at this, you would say, okay, we're going to chop off the CFT, but we're going to do violence to it. We're going to introduce some defects which fully backreact. We break the supersymmetry in half. You could ask, maybe we can retain some of this structure. Maybe something nice can be retained. It turns out it's even better than that. So let me tell you how. So we're looking at solutions which have ADS4, S2, S2, and sigma. And the simplest geodesics I can look at are the ones which are localized on a point on the Riemann surface. I'm going to hold them fixed there. And then they can spin on either one of the S2s or on both. That's all I get to choose. And geodesics which spin on only one S2 can preserve the R symmetry of the other S2. For that, they have to sit on the boundary of the Riemann surface, where the other S2 is called. choose collapsed, I can put the geodesic there without breaking any of the symmetries, and they are nice. And just from sort of representation theory, you know that these single charge geodesics sitting on the boundary correspond to absolutely protected operators in the 3D n equals 4 superconformal. With respect to the 3D n equals 4 superconformal. So they cannot just pop out and go away as they please. They're absolute. So that's the first sign that these operators are probably nice. And indeed, they are very nice. You get one single charge BPS geodesic spinning on one of the S2s between any pair of brane sources. One and only one. So between any pair of 5 branes, between any pair of 5 brane and ADS5 cross S5 region. If there's no ADS5 cross S5 region, you don't get single charge geodesic. So just from these sort of topological, in some sense, or cores features of the supergravity solution, you can tell how many such geodesics you get. And moreover, if you take these single charge geodesics, you take the PP wave limit, you take the Penrose limit, you find the exact same PP wave that you get from standard n equals 4 super. So we introduced boundaries, we broke half of the supersymmetries. But if you look at these kinds of geodesics, they want to restore the full supersymmetry of n equals 4 super. That's just what they do. And these are operators localized on the defect. So this is not some trickery of going far away from the defect. Okay. So that's a nice kind of story. We don't even need to recalculate the spectrum of string theory on the PP wave because BMN already did it for us. But it is somewhat remarkable that we get these sectors in these half-maximally supersymmetric theories which want to restore full supersymmetry. In field theory terms, the number of groups of 5 branes can be translated to what the form of the global symmetry is. Each group of 5 branes gives you a non-abelian factor in the global Lego symmetry group. And basically, from that counting, you can then determine how many such sectors you have. And because these are nice and absolutely protected, we can determine the seed operators, the thing which corresponds to this string of z's, which everything is built on. We can determine those directly from the field theories. These are sometimes 4D operators, sometimes genuine 3D operators, but those can be understood. And with hindsight, one doesn't need any holographic duals to find them, but the BMN towers on them are predictions. And in some sense surprising because the multiplets just don't need to be logic. Okay, we also get some additional 2-charge GPS geodesics. They can be placed along certain curves through the Riemann surface. I don't want to sort of say much more about them. They also come with BMN-like sectors, which don't have as much symmetry as one might expect. These curves can change and bend, and sometimes their phase transition between ending on the same boundary, ending on different boundaries, as you dial the parameters from the field theory. This is something one can look at. But the remarkable point here are these enhanced sector sectors. Okay, good. So let me go through one example in a little more detail. We're going to take this theory, which we've encountered before, evenly distributing D3 branes over a group of NS5 branes. In holographic dual, we have one group, NS5 branes, one ADS5 region. And we only get one single charge BPS geodesic, which is sitting between the NS5 brane group, the ADS5 cross S5 region. You can understand why there's only one from the fact that among the n equals 4 superangular scalars, you basically split them into 2 groups, 2 triplets, as we discussed. And the boundary conditions set one of these groups to 0, the other one couples to the 3D. By projecting out one group, you can have operators charged with respect to one SO2, SO3, but not the other. So you cannot have a seed operator charged under the SO3 corresponding to the scalars which are projected. And then you can go through basically finding the spectrum. This is an explicit expression here. It has the same functional form as the one in standard n equals 4 superangles. There's n squared, there's a Hooft coupling here. It's the actual charge. And the way the boundary conditions manifest is basically in the level space. So this is some nice very explicit information about the spectrum of these theories. One can sort of go along and study geodesic spinning on both of these tools as well. In this case, the point I want to say is that even the seed operators, the ones which are underlying the BMN power, are non-trivial predictions about the spectrum. There's a bound on the ratio of their charges, and the seed operators and the towers on top of them are things which emerge at strong coupling. And not see those in the free theories. So we're just studying geodesics, no fancy technology for doing KK reduction. You can get fairly non-trivial information about this case. Okay, so that was the simplest example for general BCFTs, particularly the ones which we use for double holography construction. You get, of course, multiple single charge sectors as we had on the initial cartoons. And then this level spacing here, if you have multiple points of single charge geodesics, each one comes with their own level spacing. And it would be nice to understand all these nice structures which we see from the holographic duals in the field theory, from the field theory perspective, and also in the spirit of reproducing things from the intermediate picture. Having these nice structures might give a good target to actually eventually precision test this double holography. Okay, with that, let me summarize. I'm not sure I need to read this out in all glory detail. I tried in the first part to sort of make the point that double holography is a tool you can formulate in string theory. It has a precise dictionary. Everything can sort of be in account. And there's a lot to explore and study regarding it. And then we had 3 stories about n equals 4 superangles with these Gaiotto-Witten boundaries, defects, interfaces, connection between supergravity duals and matrix models. Combining them, we got the one-point function. And then there are these very nice sectors, which would be nice to understand from the field theory side. Thank you.
Christoph, so do we have any questions? I have a question. So, is there part line of this kind of doubly holographic development also for ADS3? Do people think about?
There are similar. So, okay, what you want for the implementation of double holography is a number of things, right? You want some BCFTs, some nice top-down holography. Those exist in a variety of dimensions. Where it gets harder, from as far as I am aware, is the step where you isolate what's living on the defect and give it a separate holographic dual. That and understanding in field theory terms what you're actually doing. So there are similar top-down holographic duals for BCFTs in 3D, where, however, the field theory is much less understood. And so making precise what you're actually doing, how the two couple, how the gravity theory couples to the bath, that is something which is hard to make sharp there. And the similar kind of comments basically apply to 2D.
So I know that in a 3D for ADS3 there is the special class of brains, so are called the ADS2 brains, right? Which basically expand it into anti-polar points on the boundary of ADS3, right? And recently there has been a verified focus chimeras also constructing the dual corresponding dual defect in the two-dimensional CFT2. So I was wondering, that might be like a starting point for.
Yeah, that's one way to go. Right. As far as I'm aware, it's still true that you can there are these constructions based on sort of D1, D5 BCFTs, and there are duals for these constructions in Type IIB again, where you get some similar log product structure. But in those cases, if you try to hack away the ambient CFT, you basically find that the defect dual just collapses. If you go through this basically this Um, maybe this is going to take too long. But this, let me get there. So this step of, here it is, where you want to say, okay, I'm going to isolate whatever is on the defect. I want to have something which is living there, which can stand on its own feet and support the holographic tool. That's where from as far as I have seen, this doesn't work straightforwardly. It would be nice to have examples in our literature.
I see.
Not aware of a complete setup. For now.
Thanks. Rafael, I have a question. Rafael, do you have a question? I don't think he has a
He
question.
had like he had the hand.
Oh,
emoji raised.
he raised his hand. Okay.
Take it up.
Oh,
I see.
In that case, maybe we can find Christoph again.
Okay.
Thanks for the nice talk.